Hello everyone. Today I am going to present our recently published work in Materials Report Energy titled as Effect of Surface Heterogeneity on Electrolyte Stability in Magnesium Metal Batteries, Insights from Magnesium Molecular Dynamics. All of us are well aware that currently global market is captured by lithium-ion batteries. However, there are certain limitations such as unequal distribution of raw materials, safety issues, unfulfilled energy demands. Clearly, there is a need for alternatives. Among these alternatives, magnesium is one of the most promising alternative because of its high volumetric capacity, natural abundance, resistance to dendrite formation, low cost and low toxicity. Although the feasibility of magnesium-based electrochemical systems was demonstrated almost 3 decades ago, magnesium-ion batteries still remain at research stage. One of the major issues in realizing commercial magnesium-ion batteries is the poor compatibility between magnesium metal anodes and the existing electrolytes. A wide variety of salt, solvents, and contaminants get easily reduced on magnesium metal anodes due to the low reduction potential of magnesium and form a passivation layer. Unlike the lithium-ion batteries, where the SEI is conductive to lithium ion, this passivation layer does not allow the migration of magnesium ions, hence preventing the plating and stripping of magnesium. Recent developments focus on designing simple single salt electrolytes for magnesium metal batteries. Among these, magnesium carborane salt offer an excellent anodic stability and high coulombic efficiency, but its high cost and impurity sensitivity limit large-scale usage. MgTFSI is one of the most promising simple ether-soluble magnesium salt which is easy to prepare and commercially available. However, experimental studies suggest that it decomposes on magnesium metal anodes even without applying any bias, while the computational studies predict that it should be stable under similar conditions. There are conflicting reports about the reversible deposition with MgPF6 salt as well. While some studies report reversible Mg deposition with MgPF6, others show that PF6 passivate magnesium anodes, preventing deposition dissolution of magnesium. So despite the progress with different magnesium-based electrolyte, the influence of magnesium anode electrolyte interface on plating and stripping behaviors and the origin of electrolyte decomposition remain poorly understood. The root of these experimental computational discrepancies likely lies in a critical but often overlooked factor, that is, surface heterogeneity. In theory, we often model electrode surfaces that are pristine and defect-free. But in reality, the magnesium anode surfaces are never pristine, but feature native oxides, passivation, defect, and contaminants, which persist even under carefully controlled conditions. Indeed, experimental studies have shown the presence of native oxide layers that could not be removed even after polishing. So in this work, to address the effect of surface heterogeneity, we use molecular dynamics to examine different stability of different salts on various Mg anode surfaces. So basically in this work, we considered three representative systems to model magnesium electrode surfaces. First is metallic Mg, which represent a pristine SEI-free Mg anode. Stoichiometric MgO, s-MgO, which represent a uniformly oxide passivated Mg anode or an inorganic SEI layer. Now, the experimental studies have suggested that the early stage oxide layers on metallic Mg are typically thin, structurally heterogeneous, and oxygen deficient, exhibiting a higher Mg to O ratio. Therefore, we constructed a non-stoichiometric MgO surface, ns-MgO, consisting of a thin oxide layer on the top of metallic Mg substrate. In this work, all the calculations were performed using CP2K software package, PBE exchange correlation functional, and double zeta valence polarized basis set, including the Grammy D3 dispersion correction. Rest of the computational details are given here. Moving on to the results and description. First, we check the stability of the Mg-TFSI salt on metallic Mg surface. Here, the TFSI salt consists of two TFSI anion. One forms a four-membered ring with the Mg2 plus cation, hence named as TFSI4, and one forms a six-membered ring, hence named as TFSI6. We found that during the NVT simulation, both the TFSI anions remain reductively stable on metallic Mg surface. Also, the system didn't exhibit any major variation in potential energy, indicating the absence of any major structural change such as bone formation, bone dissociation, or lattice distortion, etc. Next, we analyze the time-dependent charge transfer, as electrolyte decomposition is often triggered by interfacial charge transfer. Here, we observe that within the first 2 picoseconds, there is a charge transfer of about 1 electron from the metallic Mg surface to the Mg2 plus cation. This preferential charge transfer to the Mg cation rather than the TFSI anions could be attributed to the localization of LUMO over Mg2 plus cation. After the charge transfer, there is a formation of Mg plus TFSI minus ion pair like species, and these species remain reductively stable for rest of the simulation, and there is no further charge transfer from the surface to the salt. Next, we also analyzed the stability of the isolated TFSI anion on metallic Mg surface, and we found that over the course of 60 picosecond NVT simulation, there is no charge transfer and the decomposition of the TFSI anion. We also checked the influence of electron-rich environment. For that, we added extra electron to the system and ran the simulation for extra 15 picosecond. And there also, we didn't observe any decomposition of the TFSI anion. Taken together, our findings suggest that Mg-TFSI salt, the ion pairs Mg plus TFSI minus, as well as the TFSI anion themselves exhibit poor reactivity on pristine metallic Mg surface and remain reductively stable. This is in agreement with earlier computational studies. However, it is inconsistent with the experimentally observed instability of the TFSI anions even at the open circuit conditions. Next, we check the stability of Mg-TFSI salt on the stoichiometric MgO, s-MgO surface, which is found to grow epitaxially on Mg0001 facet. Although the presence of a magnesium oxide is expected to strongly influence the interfacial chemistry, similar to metallic Mg surface, here also we didn't observe any decomposition of the TFSI anions with minimal changes in potential energy and charge transfer. These findings suggest that both the metallic Mg and the stoichiometric MgO are inadequate model for capturing the interfacial processes in magnesium metal batteries and highlight the need for more realistic models that account for passivation layers, defects, and other sources of surface heterogeneity. Next, we move to the ns-MgO surface. Here, unlike to the metallic Mg and stoichiometric MgO, both the TFSI anions decomposed within first 15 picosecond of the simulation, leading to various fluorine-containing decomposition products in line with the experimental findings. Here, the potential energy profile exhibits three sharp drops, each marking a major structural change, E1 to E2, 3. Also, a significant amount of charge transferred from the surface to the TFSI anions, leading to the cleavage of bonds such as NSOS, etc. These are the three major structural events, decomposition events. Let's look at the first decomposition events in detail, which correspond to the ns bond cleavage in TFSI 4-membered ring around 1.1 picosecond. This preferential decomposition of ns bond in the TFSI 4-membered ring can be attributed to the localization of LUMO over the TFSI 4-membered ring and the presence of anti-bonding character at the ns bond. Now, next, to better understand the mechanism of charge transfer, we analyze the time-dependent PDOs. Basically, here we looked at how the LUMO of the TFSI anions evolve with time. Here we can see that the LUMO of TFSI 4-membered ring is well below the Fermi level of the surface, which indicates the feasibility of the charge transfer. As the time progresses, the LUMO of the TFSI 4 shifts downwards and approaches towards the valence band edge of the surface. And at 1124 femtosecond, we can see there is an overlap between the valence band edge of the surface and the LUMO of the TFSI 4, marking the onset of the charge transfer. By 1130 femtosecond, the LUMO of the TFSI-4 now has become a part of the HOMO manifold, indicating that the charge transfer has occurred. Similarly, we can understand the rest of the two events, E2 and E3. To check the robustness of our results, we also checked the effect of different exchange correlation functionals and the effect of different salt configurations, that is TFSI 4-4, where both the TFSI anions forms a 4-membered ring, and the TFSI 6-6, where both the TFSI anions form a 6-membered ring with the magnesium cation. And in these cases also we observed similar findings indicating the robustness of our results. We also checked the reactivity of isolated TFSI anions on the ns-MgO surface, and we found that the TFSI anions are intrinsically unstable on these kind of non-stoichiometric oxide surface due to enhanced chemical reactivity and charge transfer, which might be the reason for the observed experimental instability. Next, we check the stability of the MgPF6 salt, and similar to MgTFSI salt, here also both metallic Mg and s-MgO surface were unable to capture the interfacial reactivity of the MgPF6 salt, and both the PF6 anions remained stable. While on the ns-MgO surface, both of the PF6 anion decomposed, suggesting the formation of magnesium chloride in line with the experimental observations. Next, we check the stability of the carborane salt, and we found the carborane salt to remain reductively stable across all the three surfaces, suggesting the high reductive stability of the carborane salt, again in line with the experimental observations. Moving on to the conclusions, we conducted AIMD simulations in this work to resolve the various experimental and computational discrepancies and assess the interfacial stability of different salts for magnesium metal batteries, and found that the decomposition of magnesium salts is not intrinsic to the salt anion itself but is strongly mediated by electron surface. We found that the magnesium carborane salts exhibit remarkable stability across all electrode surfaces, whereas the MgTFSI and MgPF6 salt undergo rapid decomposition exclusively on the reactive ns-MgO surface, driven by the electron transfer from the surface, yielding fluorine-rich decomposition products in line with the experimental observations. We use time-resolved structural analysis techniques such as time-dependent projected density of states and time-dependent charge transfer analysis to explain the decomposition mechanism. Specific to the MgTFSI salt, earlier computational studies had predicted that TFSI anions would decompose on pristine Mg surface through the formation of Mg plus TFSI minus ion pair-like species based on the static DFT calculations. But our AIMD simulation did confirm the formation of such species on the metallic Mg surface, but no decomposition of TFSI anions was observed, suggesting the reductive stability of Mg plus TFSI minus ion pair configurations on pristine Mg. Taken together, our findings help in resolving discrepancies between earlier computational studies that employed pristine surfaces and experimental reports of electrolyte decomposition, establishing that surface heterogeneity and oxide chemistry plays a decisive role in interfacial chemistry for magnesium metal batteries. Also, our work suggests that surface engineering strategies such as introducing protective coatings or efficient removal of passivation layers can suppress interfacial degradation and enhance electrolyte stability in magnesium metal batteries. I would like to thank all the co-authors in this work, all the funding agencies, Department of Chemistry at IIT Madras. Thank you all for your kind attention.